So now we've drawn all of the different conformations for butane, and now we're going to quantify their energetics. And we actually have on the third page of the note packet that you guys have that you're filling out with these online learning opportunities, there's this same chart up there. So it says like a hydrogen-hydrogen eclipsing interaction has an energetic cost of 4 kilojoules. And so on. So first off, let's talk about what is the root of that energetic cost. And remember, the two types of strains that we've mentioned are steric strain and torsional strain. And with something like hydrogen's eclipsing, so if we think about these little pink bonds as the hydrogens, there can't really be much of a steric component to that, right? Because they're so small that they're not really coming into contact. So all of that 4 kilojoules must be due to the torsional strain. The torsional strain of that interaction. So I'll put a T there for torsional. However, when we get to the hydrogen CH3 eclipsing interaction, what is a torsional interaction? Again, it's the electrons in the plane of the bond are coming into contact, or are repelling the other electrons in the plane of the bond. So that same 4 kilojoules should essentially be the torsional strain anytime that there is torsional strain. So this HCH3 eclipsing, we could say that about 4 of those 6 kilojoules is from torsional strain, so we'll put a T for that. But there also must be some steric strain, and I'll put the S as smaller because the 4 parts torsional is greater than the 2 parts steric strain. So that's what that would be. The CH3-CH3 eclipsing interaction is still going to have that torsional component, the 4, but in this case, the steric strain is larger. It's going to make up the rest of that 11, so it would be worth 7 kilojoules. So in this case, and I'll kind of try and draw lines here. So this CH3-CH3 eclipsing is going to be mostly due to steric strain, and then a small t for the torsional strain. And then lastly, in a gauche interaction, the electrons aren't even lined up in the same plane. Remember, they're staggered, so that has to be entirely a steric interaction. So those are where that strain is coming from, why they have an energetic cost. So now we're going to start looking at the different conformations that we filled in on the last page to say what their energy will be like. So the first conformation that we had, so number 1 on that last page, was the anti-staggered conformation. And it's where we started. So it's at 0 degrees. So 1 was 0 degrees, the dihedral angle. We didn't, that 0 degrees is talking about how much we rotated. So where we started at 0 degrees, we actually have none of these interactions. If you go back on that page, there's no torsional strain because nothing is eclipsing. There's no gauche interaction. So we'll just write that there's no strain at 0 degrees rotation. So that's starting out right here. This is 0 degrees. So what happens at 60 degrees? Again, our second conformation did a 60-degree turn, and then we had the different groups eclipsing one another. So the second conformation that we had was 60 degrees, and actually we're going to fill in this table at the same time that we're doing this. So go ahead and on page 3, fill in these same values for energetics over here, and add those the dihedral angles are already on there. But at a 0 degree dihedral angle, this is where we are on the graph. We're right here. But when we went up to 60 degrees, if we look at that conformation we have an HH eclipsing, so that would be worth 4 kilojoules. We also have, if we go back and look at that second conformation, we have an H eclipsing with a CH3 and another H eclipsing with a CH3. So we have 2 of these HCH3 eclipsing interactions. So that's +6 + 6. So that's 16 kilojoules of energy. So when we rotate to 60 degrees for our second conformation, that's going to put the energy of the molecule at that point. So with a 60-degree turn, we went from there to there with our energy. So we went much higher in energy. On the third conformation, go back and look, was staggered gauche. So the staggered gauche conformation has a CH3 gauche interaction. So that's 120 degrees. And that is going to be worth 3.8 kilojoules. So that third conformation brings us back down to this level right here. So another 60-degree turn to 120 total degrees so far. We are at 120 degrees of that dihedral angle. To get us to that midpoint, number 4, number 4 was a 180-degree turn. And at that 180-degree turn, if you look at that one, that was the fully eclipsed conformation. So we had a hydrogen eclipsing with a hydrogen, another hydrogen eclipsing with another hydrogen, and we also had a CH3 eclipsing with another CH3. So essentially that gave us 11 from the CH3 eclipsing with the CH3, and then 2 of these HH eclipsing interactions. So 11 plus 4 equals 19 kilojoules. So at that 180-degree dihedral angle, we go up to the maximum of the energy plot. And then we're just going to keep turning 60 degrees at a time, just like we did on that last page. So this would be a good time for you guys to pause the video, try to work out the remaining energies and how that relates to this graph. And then once you restart it, I will have it filled in at that point. Again, you got it all right, hopefully. But here I filled in the remaining energies for those last few, and I added those 3 points to the graph. If you're having a hard time with this, definitely talk to me. I'd be interested in helping you figure this out. But hopefully it makes sense. Yeah, again, let me know if you need help. And the last thing that we'll do in this video is just the last part of page 3. So we have to be able to work with these Newman projections just like we would with any other molecular representation. So the final molecule on page 3 is a mixture of a Newman projection with a skeletal structure. So we have to be able to take that structure and name it, give it a name using IUPAC nomenclature. So I'm going to, again, allow you guys the time to pause it and then work out that name and then unpause. Here's our Newman projection on the page 3 of our notes at the bottom. So the first thing that I would do is probably take this Newman projection and turn it into a fully skeletal structure. So so far what we've been doing is the opposite. We've been taking skeletal structures and converting them to Newman projections, but we have to be able to work both ways. Give yourself a minute to try and do that conversion. Convert this from a Newman projection into a skeletal structure, and then come back to us. All right, so let's do this. So what I'm going to do is pretend like I'm just looking at this like I would be with a model. So if I was looking at this with a model and I was trying to convert into a skeletal structure, we know that this carbon and the carbon behind it are connected by a bond. So we can draw those 2 carbon atoms there. What I've always done is look at what is closest to my forehead. So this front carbon, my forehead and my chin. So this front carbon, the thing that's closest to my forehead is this hydrogen here. So if I turn the molecule sideways like this, that hydrogen is going to have to be going up, because that's what it would do. What about if I'm essentially turning the molecule like this, and that hydrogen's going up? So when I do that, whatever's on the right is going to be coming out at the camera, and whatever's on my left is going to be going into the plane. So this is on the right, this CH3. So that CH3 is going to be coming out now, and this CH2, 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 CH3 is going to be going into the plane. So CH2, 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 CH3. So that's that. What about the back side? Well, on the back side, this hydrogen is at my chin when I turn that sideways, so it should be going down like that. What's on the right should be, because we're turning it like this, again, should be coming out. So that is those groups because they're on the right, and then whatever is back here, whatever's on this side is going to be going into the plane. So that's how I convert from Newman projection to skeletal. I kind of take what is in the plane and put that all in the plane. So everything that I put in this square here, all of that stuff, this square is all of this stuff right here. So that's kind of how I do that conversion. So it's a skill that you're going to have to work on. So definitely dedicate some time to that. So now that we've converted that structure into the skeletal format, you should just be able to use all the standard naming things that you've done before. And so we're going to look for the longest chain, and that would be from here down. So let's get a different color. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 9 carbons long, so it's a nonane. So nonane. And then we need to describe where the substituents are. There's a substituent on position 3 and position 5. They're both just methyl groups, so this would be 3, 5, dimethyl nonane. And this doesn't need a space there. That could be all one word. So that's that process. You're going to get some more practice on that, and let me know if you need some help with that.